Welcome to the first of a series of lectures on scanning probe microscopy. This is a catch-all term that refers to a whole family of different imaging techniques which have revolutionized our understanding of surfaces at the nanoscale and our ability to engineer them. So it's an area which is characterized by a whole series of different acronyms. You can see a few of them here. We're going to see a lot more. Essentially, three of these acronyms are interchangeable. It's something we're just going to have to get used to. So what is a scanning probe technique? In general, it's a way of taking an image of a surface which is not optical and which provides a mechanical picture of the surface of interest. So we have some sort of probe, indicated here by the blue triangle, which is scanned over a surface which essentially can be of any material whatsoever, as long as we can get it into the microscope itself. We refer to these instruments as microscopes. It's a bit of a misnomer because they're completely unrelated to optical techniques such as SEM and conventional optical microscopes. So we can think of the technique being analogous to that of an old gramophone player, where some sort of needle is dragged over a surface and the topography of the surface gives us a signal. So in a record player or gramophone, that led to sound being played out. And indeed, during the 70s, people used gramophones to record surface topography. So they took the audio file and they used that as a measurement of the surface topography. Since then, the development of materials and electronics has permitted us to come down to a much lower level so that we can actually do this thing down to atomic resolution. So here's a few examples of the different types of scanning probe techniques that are available. This is a minuscule selection. There are literally probably hundreds by now of different approaches for getting different types of information about the surface. Those that we'll be looking at today are, of course, AFM, STM, LFM, CFM, and that's about it from this list. But there'll be a few more.
Your first words will be, there will be a few more, and then you'll continue on. Go back to full screen. So now I can really easily cut this together. You like to start your sentences with, that goes bing.
Ah,
on the
that's something I was happily unaware of.
It's really hard. You don't hear it in a normal conversation. You'd never notice it. And it's going to be hard for you to break the habit. See if you can, because they're noticeable. They're a lot more noticeable on a...
Sorry, what were my first words going to be? There are many more.
There are many more.
Yep.
And there are many more. There are many more. And then you can just go on to your next slide. So stay right where you are. Say, there are many more in the same tone of voice, and then I can just butt cut those two things together. You can make that. I'm just needing All right?
All right.
We ready?
Ready?
There are many more. So scanning probe microscopy can trace its history back to
Can we do that again, Mark?
Yep. The whole over transition.
Yes, please.
Mm-hmm.
Okay.
And there are many more. So scanning probe microscopy can trace its history back to 1981, when Gerd Binnig and Heinrich Rohrer invented the first scanning tunneling microscope, which allowed us to see three-dimensional objects down to the atomic level. For this, they were awarded the Nobel Prize already in 1986, which is a very fast turnaround and reflects the enormous importance that this technique has had. Coincidentally, in 1986, they invented the atomic force microscope, which is a slightly different type of probe, which is applicable to more types of surfaces than just conducting surfaces. And perhaps, well, if it had been possible to get the Nobel Prize twice for essentially the same thing, Binnig might have been worth a second Nobel Prize for that. So when they got the news, they were celebrating at a ETH football match. So I don't know if they won or lost, but they certainly felt like winners at the end of it. So what are the principles of scanning probe? What is it that we need? What are we talking about? So what we need is some means of rastering a probe over the surface to generate the mechanical image. So we need some sort of probe, and we need something to literally drive the scanning probe, referred to surprisingly as a scanner. Now the scanning is achieved due to developments in piezoelectric materials, which are materials that change their dimensions in response to an electric field. So if we apply, for example, to quartz and a voltage, we can either contract or expand in the direction of interest, and we can use this to control the spatial position of a probe with great precision, down to literally angstroms. So you see in the picture here an example of a tube scanner, which is what we use to, in general, scan the surface under the AFM probe. The Z scanner, by applying a voltage, allows us to move up and down, and X and Y allows us to raster the tube left and right, which allows us to generate a sweeping image. Okay, so the size of the tube essentially determines the range of movement. So for very, very, very small objects like atomic resolution, you probably want a small scanner to reduce noise and just have very, very small movements. If you're interested in larger features of the micron size, then you need a larger scanner, a longer tube, and that tends to reduce the resolution of the system due to picking up extra noise. But because we're applying a voltage to a tube, we tend to, in most instruments, be sweeping the tube left to right, and this means that the scanner on which our sample is mounted is describing an arc. So we need to have our computer controlling the signal to the Z direction to keep the height constant. So we can already see at this point that this technique is very, very intensively dependent on the ability to control the experiment by computer. And in commercial instruments, this is all automated. So the other thing we need to do is have some sort of measure of the probe surface interaction. So in the case of the scanning tunneling microscope, that is of course the tunneling current between a conducting probe and the surface of interest. So this sharp tip is scanned over the surface in some way. The electric current between the tip and the surface is measured, and that provides the feedback to control the height of the substrate with respect to the tip, which provides the information to give you a topographic image of the surface. Essentially, the movement of the piezoelectric scanner up and down gives you the mechanical picture that you need. In atomic force microscopy, instead of using a current, which requires obviously conducting or semiconducting materials, what we use is the force, the deflection of a spring, often known as a cantilever, to which the sharp tip is attached, which you see here. And this is where we get the name atomic force microscope, because it's ideally the contact of the electron shells of the outermost atom on the tip coming into contact with the electron on the outermost atoms on the surface, the Born repulsion. Not everyone calls it the atomic force. There's a bit of controversy about that, so a lot of people prefer scanning force microscopy. And then we track the position of the cantilever, so the amount of deflection as a result of the topography and the interaction with the surface, by reflecting a laser off the back of the cantilever. Although the movement of the cantilever may only be of the order of angstroms or nanometers, the path length of the laser from the laser here to the detector, which detects the movement across this split photodiode, is of the order of centimeters. So minuscule changes in the angle of the cantilever can be detected very readily. So we have very, very sensitive control of the movement. A less common feature of AFM, which is something that interests me a lot, is the use of colloid probes. So it's not necessarily for characterizing surface topography, but it does give us a lot of information in some cases about material properties. And instead of using a sharp tip on the surface, we actually attach a fiber or particle of which is the material of interest to the AFM, and we use the force measuring and translational properties of the AFM to measure things like adhesion and material properties in that way. And the advantage of that is that we can actually probe the material properties of materials of interest instead of probe materials which typically come in only one or two materials. One of the things that characterizes development of SPM is that it's largely driven by commercial players. So there's a few big commercial AFM developers out there. A lot of the novel techniques and pushing the envelope of the technology are being done by them in collaboration often with leading universities. And if you're interested in particular imaging techniques or particular materials and how to use AFM with them, what you'll find is that the manufacturers have very, very professional homepages which give you instructions how to treat and study the material that you're interested in. If you're interested in more detailed understanding of SPM, then we have an 8 ECTS course at KTH, which is run by Professor David Haviland of nanophysics, where you get a full introduction to all the mechanical, electronic, essentially all the nuts and bolts and tools of SPM, rather than just the application to materials examination, which is what we're concerned with here. And in the following lectures, I'm greatly indebted to many people who've kindly provided me with slides and material, particularly David Haviland and Professor Mats Götterlid, who's KTH's probably leading STM professional.